As in the previous part, we talked about the origin of the black holes and discussed some things about their nature and how the laws of physics work on them. Now let's dig a little more into the things that are part of these black gravities and many more things about the cosmos. As the appearance of the black holes looks like a ring of light and a pitch dark thing right in the center. This boundary of the black hole, or called the event horizon, is formed by rays of light that fail to get away from black hole's singularity and is revolving like just any planet around a huge gravity body. The more the matter goes into the singularity of the black hole, stronger the strength of the black hole becomes. It can consume bodies of cosmos or even the small black holes as well. With the increased strength, its event horizon will get bigger and bigger, and the ring of the light will appear thicker. This even horizon actually shows the entropy of the black hole. Entropy in simple terms is the state of disorder in the system, where there is negligible stability. And as the time passes by, the entropy keeps on increasing, and there will be more instability. This is called as the arrow of time, and this gives a direction to time and distinguishes past from the future. This disorder increases with time because we measure time in the direction in which disorder increases. It's just like looking at a piece of a broken glass and knowing that once these pieces were all together in a perfect glass. We know that broken glass is a future and a complete glass was its past. We never see a broken glass being fixed and turning into a perfectly fine glass. This shows that disorder increases as the time passes by. Black holes work on the principle of second law of thermodynamics. The law states that the black hole will emit radiation in form of particles, like any other hot body. The temperature and emission of the particle would depend on mass of the black hole. Higher the mass, lower the temperature, and bigger the black hole, less the emission of the particle. The emission of the particles and radiation was in the form of gamma rays and X-rays of very short wavelengths of luminosity, and it eventually was also a proof of our calculations and discovery of general relativity and quantum mechanics. If a person falls into a black hole, its mass will increase, and the energy equivalent of that extra mass will be returned to the universe in the form of radiation. This follows the Einstein formula E equals to mc squared, where energy is equals to mass of the matter times the square of the speed of the light. This conversion of matter into radiation and particles comes at a cost of the energy which comes through the black hole. A small fraction of the mass of the black hole is used as that extra energy required for that conversion. So, in some 100 billion years, this black hole keeps losing his mass and will eventually run out of its own mass and will die with a huge explosion. It is calculated that black holes are rare in the universe, and on average, there cannot be more than 300 little black holes in every cubic light year in the universe. They pretty much make about 1/millionth of the average mass density in the universe. The classical theory of general relativity predicts that the universe should begin with a singularity where the curvature of space-time is infinite. This gives a good explanation and description of the universe. One has to use the quantum theory of gravity to understand how the universe began. The universe would have started in a smooth and ordered state and would become lumpy and disordered as time went on. This would explain the existence of the thermodynamics arrow of time. In the next and the last part of this book, we'll see about how the scientists solved the theory of the origin of the universe and how they all overcome the arguments on it. And eventually we'll see what Stephen Hawking meant by the term theory of everything. The next part will conclude the entire book. We thank you for being with us throughout these chapters. Thank you.